I wouldn't call this a solutions video. I just want to make sure that we have an opportunity to sort of highlight what the most important points were that you were supposed to get out of this tutorial. These two charges, the small plus q and the large plus q, are each positive, meaning that they will repel one another. So the forces are in this direction. And the question about which one is stronger than the other or are they equal could be answered by saying that Coulomb's law looks the same in both places, so the force has to be the same magnitude. This also could have been answered by noting that this is a Newton's third law of force pair. If force large Q is pushing force small q, then force small q is pushing force large q the same amount in the exact opposite direction. Either way is a legitimate way to answer this question. And of course, we've talked a little bit already about what it means if the distance is changed. So if the distance between these two charges is doubled and the charges themselves remain the same, then the force between them will be 1/4 of the original value. If that doesn't make sense to you, please refer back to our original lecture videos. In this slide, I don't completely agree with either of the students. I think student 1 is hitting on the right idea that as you increase the number of charges that are affecting the little q, the forces will have to add to each other. But student 1 is forgetting that these will add together as vectors. Student 2 is kind of hitting on that idea, but student 2 is oversimplifying. For example, this charge on the right will cause this, what I've drawn in as a red force vector, and it has this x component here and this y component. So a component of the force in the negative x and a component in the positive y. The blue charge would have similarly a force on the far right here, the blue one, with a positive x component that I'm drawing in now and the positive y that I had drawn in. Student 2 is correct that the x components will add to 0, but is forgetting that the y components will still contribute in the positive y direction for a net force that will be in the positive y direction. And again, student 1 had failed to account for the fact that if these three forces are equal, the red, the green, and the blue arrows, only the green one is pointed directly in the y. The red and the blue have the same magnitude as the green one, but will not contribute as much in the y direction. So each of these students has some part of the right answer, and neither one of their statements is actually completely correct. I think on this ranking task, a similar process of drawing the force vectors onto little q can be really helpful for us to understand exactly what's happening. Now, the student groups who I spoke with during the tutorial were generally able to piece together that case B must be greater than case A, which is in turn greater than case C, if we're ranking these by the net force on the small charge q. And that is because in case A, the charge on the left and the charge on the right don't completely contribute in the same direction as the charge in the middle. So their force vectors will add together to a positive y force vector, but not as much as in case B, where the +3 charge is all in one spot. Case C is less than case A because the geometry is very similar, but the charge on the far left and far right are farther away in case C than they had been in case A, meaning that the amount that each of them pushes on the little charge q is less in C than it had been in case A. The real issue is case D. A lot of groups weren't sure exactly where to rank case D, and I think that's a very understandable situation to be in. So let's take a look at how I would approach this. In case D, I have this positive 3q that will repel little q, and that is therefore exerting a force in this direction. I then have the negative 3q over here that is exerting a force on little q, but it is positive little q and a negative 3q in this case, so it will have an attractive force of that same magnitude, but in a different direction. If you think back to how we do vector addition with a tail to tip or parallelogram method of vector addition from Physics 140, it means that we will have a net force on little q that is something like this. And this magnitude has to be more, mathematically, than either of the individual vectors that I just drew, the blue one or the red one. Well, remember that that blue one is the repulsion from the plus 3q onto the little q. And that is case B, is the plus 3q to the little q. So if in case D, the green vector net force is greater than the blue vector, which is only contributing to it, then that must mean that case D has greater force on little q than case B does. And B was greater than A, and A was greater than C. I feel that if you understood BAC correctly and you were a little bit confused by case D, that is exactly what this slide was trying to get at. And it is a bit of a subtle point about how to deal with these types of problems. You don't want to look at the plus 3q and negative 3q and say they add up to 0 or they cancel each other out. We're not talking about whether the charges would add to 0 together. We're talking about whether they cause forces that add together to make a larger force or a smaller force. And in this case, it's a larger force than in case B. The groups who I did speak to about this page were doing really well with it, because the point of this question is to emphasize that Coulomb's law will provide you either a positive force value or a negative force value, and that positive or negative tells you whether the force is repulsive or attractive, but it does not tell you whether the force is to the left or to the right until you stop and look at the arrangement in your particular system in that question. So this positive Q pushes this other positive Q in this direction, and then this negative Q pulls this positive Q in this direction. And if you were to do the calculations, you would find that the blue force vector is a positive value by Coulomb's law, and the red force vector is a negative value by Coulomb's law. And that doesn't seem to make sense from what we know about vectors, because the two of them are supposed to be pointed in the same direction. And that's the whole point of this slide, is to emphasize that Coulomb's law, force vectors being positive or negative, does tell you something about the direction, but it doesn't tell you directly what the direction is in Cartesian coordinates. You're going to have to be smarter than the math. And then on this slide, much like at the very beginning of the tutorial, what we're trying to get at here is if in case E we take the charge plus Q and evaluate what's happening to little q, we would understand that it is pushing little q off to the left. But if we take this positive Q and spread it out over an arc, that's what case F is really taking the same amount of charge and spreading it out. Then we end up with all of these smaller force vectors that will add up together to be a net effect pushing the little q to the left. But we have introduced these components in the positive and negative y direction. And those components will add to 0 in the negative y direction, but more importantly, they don't contribute to a perfectly negative x direction. So the net effect in case F is less of a force to the left than it had been in case E. I hope all of this makes sense, or at least helps to make sense. If you have questions about this tutorial or the related material still, then obviously please do contact me.